24. Sorry about the mic. We're going to be looking at a rule for differentiating a composition today. So before we do that, there's a couple things I wanted to talk about. The first thing was just to review the table of derivatives here. Notice that we're building up quite a table. So I've got them listed here. On the left are specific functions, and on the right are the general rules over here. These are the kind of general rules over here, and these are specific functions over here, right? Okay, so it's probably a good idea to have these memorized. So for example, if we just go through them real quick, the derivative of a constant is 0. Derivative of x to the n is n x to the n minus 1. That's the power rule. Derivative of the exponential function is just the exponential function. But a to the x, right, the derivative of that is going to be a to the x times the natural log of a. And so notice that these two are exactly the same, right? It's just that in this case, this is the a to the x is the more general. Okay. Oops, sorry about that. Down here we have our three main trig functions: sine, cosine, and tangent. And I hope we have those memorized now. Derivative of sine is cosine. Derivative of cosine is minus the sine. So remember, the derivative of the co-functions have a negative sign in front. Derivative of tangent is secant squared. Derivative of cotangent is minus cosecant squared. And then derivative of cosecant is minus cosecant cotangent. And derivative of secant is secant tangent. Okay. Also, we have a constant. The derivative of a constant times a function is the constant times the derivative of a function. The derivative of a sum or difference is the sum or difference of the derivatives. This is the product rule. The derivative of f times g is f prime times g plus f times g prime. And then the derivative of the quotient, f divided by g, is f prime times g minus f times g prime divided by g squared. Good. Okay, so these, if you don't have these memorized yet, you might use some flashcards and get them memorized. Okay. We'll try to have a video with more drill practice on just differentiating different functions. Okay. Alright, so that's the setup for today. Let's go into the main topic now. The chain rule. So this section is actually very short. It's short for me to discuss, but I think it takes a lot of practice to get used to it. And so the way we start with the chain rule is we have to be able to, our primary skill here is to be able to identify a function composition, because the chain rule is set up for function composition. Okay, we've already done this back in chapter 1, but let's go ahead and do some review. Some review. For example, if f of x equals the sine squared of x, rewrite as f of g of x. Right, it's a composition of two things. So what's that going to be? I'll give you a hint. If you want to rewrite the way this is actually computed, right? And I think there you can see it. So therefore, the inside function would be the sine function, and the outside function would be a square function. So therefore, we would write f of x equals x squared, and g of x equals the sine of x. Okay, now this might actually be confusing. There's another way to write this, and that is we could write as f of w of x, where we use we're going to use a different symbol here. Here, I'll show you what I mean by that. we can write it as f of w equals w squared using a different symbol for the input, and then w of x would be the sine of x. See these two decompositions being the same thing, but this one is maybe a little bit less confusing because we're using a different symbol for f, right? We're saying that f depends on w, not on x. Okay, so we're going to try this on some others as well. How about 3x plus 1 to the 4th power? Let's write that as a composition. I'll give you a second. Okay, so we have an inside function here of 3x plus 1, and so we would write g of x is 3x plus 1, and then our f of x, our outside function, we can write either as f of x equals x to the 4th, or you could write f of w equals w to the 4th, right, with g of w, g of x. Better be careful. I want to be consistent with my notation. If this is w over here, oops, if that's w over there, then I want to use w over here. Okay, good. And actually later on we're going to see why this notation is helpful. How about another one? How about the exponential function? E to the x squared plus 5x plus 1. Okay, so our outside function looks like e to the x, right? Inside function looks like the polynomial. Or you could write it as f of w equals e to the w, where w is equal to x squared plus 5x plus 1. Okay. Maybe, well, so see the handout on compositions. That'll give you lots more practice. Okay, good. All right, so now what do we want to do? We want to take a look to see what the derivative is for a composition. So let's see, how am I going to do that? Let's use the definition. And so the derivative of f composed with g is equal to the limit as h goes to 0 of f of g of x plus h minus f of g of x divided by h. Okay, now I'm going to do a little bit of an algebra trick. Notice that f doesn't depend directly on x, f depends on g. And so that's what I was trying to write up here. I was trying to emphasize that f doesn't depend in this example on x. F actually depends on an intermediate w, right? And so one way to really get at that is I'm going to multiply and divide by the same number. And so I'm going to multiply and divide by g of x plus h minus g of x. Okay. And so what we have here now, notice that this first expression is expressing the rate of change of f in the numerator with respect to its whatever it's acting on in the denominator, right? And so this first expression here is actually, in taking the limit, is going to be the derivative of f, but evaluated not at x, but at g of x. And this second expression is g prime of x. And that is the chain rule. Okay, now there's a different way of writing the chain rule that may be helpful. So it's probably good to see it in both ways. So if we have f of w, and w is a function of x, the rate of change of f with respect to x is going to be the rate of change of f with respect to its variable w, but then you have to multiply by the change of w over the change of x. And so this is Leibniz notation. And notice that you can kind of think of these as fractions, where the dw's look like they're going to cancel each other, right? So these two dw's look like they're going to cancel each other, and then you would just be left with your df over dx. And thinking of it that way actually works fine. And in fact, this way may be easier to think about because, well, let me pause there. Maybe we should go through some examples before we come back to that. And I'm at my time now. It's been 11 minutes, and so we'll pause there and we'll come back with a new video with just lots of examples of the chain rule.